The bridge was gone, the attack schedule was not. In the fighting along the Volturno River in October 1943, German pioneers were doing what their doctrine demanded. As units pulled north, the engineers broke the roads behind them. Bridges were dropped. Culverts were blown. Mountain roads were cratered. Rubble was pushed into routes that heavy vehicles needed to use. The purpose was not to make Italy impassable forever. It was to make every mile cost time. Then, before dawn, from somewhere down near a ruined crossing, came a sound that did not fit the German calculation. A crawler tractor was working in the dark. Its blade bit into the bank, shoved loose soil forward, backed up and pushed again. Men were already clearing, carrying, measuring, and building around it. The bridge might still be in the river, but the obstacle was already being rewritten. That sound mattered because the German defense of Italy depended on a clock. To understand the clock, picture a German pioneer officer on the North Bank. He is a composite, not a documented individual with a surviving diary entry from this exact crossing. He represents the engineers whose job was to destroy routes, mine the approaches, and leave the advancing allies with a sequence of physical problems. For him, a successful demolition was a calculation. Explosive placed against the right pier could make a bridge useless in minutes. If the wreckage fell badly enough, if the banks were steep enough, if the road network offered no easy alternative, the attacker would need time to survey the gap, clear mines, bring forward bridging equipment, cut approaches, organize traffic, and protect the work. That delay was the product. German forces in Italy could not rely on matching Allied material strength. Their defensive system instead leaned heavily on geography. Rivers, ridges, narrow valleys, mountain roads, and towns built into hard ground. Field positions could be improved while the enemy was still wrestling with the obstacle behind them. Guns could move, units could reorganize, a new line could be prepared. The destroyed bridge did not have to stop an army. It only had to move that army's timetable to the right. And Italy seemed made for that kind of warfare. The peninsula forced movement through a limited number of usable routes. Rivers cut across the direction of advance. Roads climbed slopes where one crater could block a column. Demolitions could turn a retreat into a sequence of engineered pauses. Mines and booby traps made repairs slower and more dangerous. Even a small obstruction could grow into a traffic problem when trucks, artillery, ambulances, fuel vehicles, and bridging equipment all converged on the same narrow road. For the defender, that friction was valuable. But the Americans brought an engineering culture that changed the value of friction. The important machine was not exotic. It was a heavy crawler tractor with a blade, the kind of earth-moving machine that had already become familiar on civilian construction jobs in the United States. Machines in the Caterpillar D7 and larger classes could push soil, rubble, and broken road material with a force that replaced enormous amounts of hand labor. The machine alone was not the solution. That distinction matters. A bulldozer could not span a deep river. It could not clear every mine safely. It could not guarantee protection from artillery. It could not turn an unsupported crossing into a highway by itself. What it could do was attack the slowest physical steps around the crossing. It could carve an approach where a bank was too steep. It could push broken masonry out of a road. It could fill a crater enough for following vehicles. It could cut a diversion around a demolished section. It could prepare the ground where a temporary bridge had to begin and end. And behind the dozer came a larger system. American combat engineers worked with bridging equipment, boats, pontoons, prefabricated components, trucks, cranes where available, mine-clearing teams, and large numbers of soldiers trained to build under pressure. One of the most useful systems was the Bailey Bridge, a British-designed modular bridge that Allied troops could assemble from prefabricated steel panels and launch across a gap without waiting for a permanent structure. The Bailey Bridge did not make rivers disappear. It changed the sequence of work. A destroyed permanent bridge no longer meant that the attacker had to rebuild the old bridge before heavy traffic could move. Engineers could create a temporary military crossing, connect it to hastily prepared approaches, and restore movement while the ruins were still visible below. The dozer mattered because it connected that temporary bridge to the road network. A military crossing is not one engineering problem, it is a chain of them. First, men and machines have to reach the water. A demolition may leave the old road ending in a wall of rubble. The shoulders may be mined. The last stretch may be too narrow for trucks carrying bridge material. If the approach cannot carry traffic, the bridge site is useless no matter how quickly the span itself can be assembled. Then the banks have to work. A truck or tank cannot climb a slope just because a map shows a road on both sides of the river. The approach angle, the bearing strength of the soil, the width of the lane, and the condition of the exit all determine whether vehicles can cross without becoming a second obstacle. This is where earth-moving machinery could save hours of labor. Then comes the bridge or ferrying system itself. It has to carry the loads the army actually needs, not merely put a few infantrymen on the far bank. A crossing that passes men but not ammunition trucks, artillery, recovery vehicles, fuel or armor does not restore operational movement. And after the first vehicle crosses, the problem is still not finished. Traffic has to be controlled. Damaged vehicles have to be pulled clear. The road behind the site has to remain open so bridge material can move forward while combat traffic moves through. A narrow crossing can create its own traffic jam faster than the enemy can create one. This is why the image of a single heroic machine is misleading. The bulldozer was valuable because it shortened several links in a much longer engineering chain. It helped the rest of the system arrive at the point where movement could resume. A bridge without usable approaches was only steel over water. A cleared road without a crossing was only a road to the riverbank. The power came from the combination: earth-moving machinery, modular bridging, organized engineer labor, and a command system willing to push that labor close to the front. That combination changed the German clock. The best way to see the change is at night. A German demolition team could leave a crossing believing that darkness had closed the workday. The road was broken. The bridge was down. The next serious Allied movement should have to wait until the obstacle had been inspected and dealt with. But the engineers on the other side had a different incentive. If the crossing could be prepared during the hours when the combat units were not yet moving through it, then engineering work did not have to become a separate pause in the offensive. The pause could be absorbed into the night. So the work began while most of the battlefield was still dark. Men checked the approaches. Mine teams dealt with what the Germans had left behind. A dozer pushed a ramp into shape. Trucks brought forward bridge components. Crews assembled what they could near the water. Others improved the road behind them so the first vehicles would not jam the route the moment it opened. The scene was not clean or effortless. It was exhausting, noisy, dangerous work done close to enemy positions. German artillery could search for the sound. Mines could stop a machine that seemed unstoppable from a distance. A broken track, a mechanical failure, soft ground, rising water, or a bank that would not hold could ruin the plan. Engineers working at a crossing were concentrated around exactly the place the enemy expected them to be. There was no magic in it. Night work carried its own trade-off. Darkness could reduce direct observation, but the machinery announced itself. Engines, metal, shouted instructions, and repeated movement near a known crossing gave German defenders clues about where the effort was concentrated. Engineer troops were not protected by the fact that their job was called support. At a bridge site, support work could become the most exposed work on the map. The crews also had to build for the army that would arrive after them. A crossing that opened at dawn and failed under the first heavy traffic had solved nothing. The road surface had to survive repeated loads. The approaches had to keep their shape. Temporary bridging had to be used within its limits. Machines needed fuel and maintenance at the very moment they were being worked hard in mud, water, dust, and broken stone. That cost is part of the story because it prevents the engineering advantage from becoming a myth. American resources were immense, but resources became speed only when organized labor turned them into a working route. There was only a different relationship with time. For the German pioneer, demolition was meant to create a guaranteed interval between destruction and renewed movement. For the Allied engineer, that interval was a work window. The difference sounds small until an army is retreating. If a destroyed bridge buys 2 days, the defender can plan around those 2 days. A battalion can move. A battery can change position. A headquarters can shift. A new roadblock can be prepared farther north. Men who have been marching and fighting can sleep. If the same obstacle buys only part of a night, planning changes. Units cannot assume that the river behind them will protect the next morning. Rear guards have to stay engaged longer. Artillery must be ready to fire on repair sites. Demolitions need mines, covering fire, and repeated defense if they are to produce the delay once expected from the obstacle itself. The attacker has not made terrain irrelevant. He has made delay more expensive to guarantee. That is the deeper point of the bulldozer in Italy. It did not defeat a bridge demolition by being stronger than explosives. It changed how quickly the attacking army could turn destruction back into movement. The German engineer was working with a subtraction model. Remove the bridge, remove the road, remove the culvert. Each subtraction should reduce the enemy's speed. The American engineers answered with construction capacity. If the original route was gone, they did not always restore the original route. They built a military solution around the loss. A ramp could replace a finished approach. A temporary bridge could replace a permanent one. A bypass could replace a cratered road. Rubble could be shoved aside instead of carried away by hand. The solution did not have to be elegant, it had to carry the next vehicles forward. This was an industrial advantage expressed at the level of mud, steel, diesel, and exhausted men. It also changed what counted as a usable road. A peacetime engineer might want a stable grade, drainage, a finished surface, and a structure designed for years of service. A combat engineer often needed something narrower and more urgent. A route that would carry the next required load for as long as the operation demanded. Temporary did not mean careless. It meant designed for a different clock. That distinction favored an army able to bring large quantities of standardized material forward. Instead of treating every destroyed bridge as a unique civil engineering project, military engineers could use repeatable systems, familiar equipment, and practiced procedures. The terrain remained unique. The response became less unique. That is one reason the defender's demolition could lose value even when it was technically excellent. The Germans might destroy each bridge according to its local structure. The Allies increasingly approached the aftermath with a set of adaptable tools that did not require the original bridge to be restored in its original form. The United States entered the war with a vast civilian base of heavy construction. Road building, dam work, highway construction, agriculture, and other large construction projects had created operators, mechanics, equipment, and a national habit of solving problems by moving material at scale. The Army could draw on that experience. It still had to turn civilian capability into military engineering. That meant spare parts, fuel, transport, training, maintenance, traffic control, mine clearance, protection. Men who understood that a machine working 10 miles from the front was useful, but a machine that could be brought to the actual blockage at the right moment could change an operation. The Bulldozer became memorable because it made all of that visible. A truck carrying bridge panels looks like logistics. A planning table looks like staff work. A mine-clearing party is often invisible until something goes wrong. A dozer physically changes the ground in front of you. A bank becomes a ramp. A crater becomes a rough lane. A pile of masonry becomes a shoulder beside the road. The evidence is immediate. That visibility could make the machine seem more powerful than it was. The source of the speed was not one blade. It was a network of engineers and equipment working as a system. By 1944, the logic went even farther. Bulldozer blades were fitted to armored vehicles, including Sherman-based tank dozers, allowing earth-moving work to reach ground that was too exposed for a soft-skinned construction vehicle and crew. Again, the purpose was not to turn a tank into a construction miracle. It was to reduce the number of situations in which enemy fire could preserve an obstacle simply by preventing engineers from reaching it. That is what mechanized engineering did to the old arithmetic of delay. It forced the defender to keep paying for the same obstacle. Blowing the bridge was only the first payment. To make the destruction last, the Germans had to cover it with mines, artillery, direct fire, additional demolitions, or positions that could stop repair crews from working. An obstacle left alone was becoming less reliable as a unit of time. This did not mean the German delaying strategy in Italy simply failed. The distinction is important. The campaign remained slow, costly, and dominated by terrain. Rivers still mattered, mountains still mattered, weather still mattered. The defensive lines south of Rome imposed severe delays and heavy fighting. No honest history of Italy can claim that bulldozers made the geography disappear. What they did was remove certainty from one part of the German calculation. A demolished crossing could no longer be assigned a fixed value merely because the physical structure was gone. The value now depended on what the other side could build, how fast it could build it, and whether German fire could keep the engineers away long enough for the obstacle to matter. That is a subtler victory than saying a machine defeated a strategy. It is also more revealing. War is often described through weapons that destroy: guns, bombs, tanks, aircraft. The combat engineer works in the opposite direction. His power comes from restoring function under conditions designed to make function impossible. A road is cratered. He restores movement. A bridge is dropped. He creates another crossing. A bank is too steep. He changes the bank. A route is mined. He opens a path through it. The work does not look like conquest, it looks like labor, and that is why it could be psychologically unsettling to the men trying to delay it. A German pioneer could look at a successful demolition and see proof that he had changed tomorrow's schedule. Then before sunrise he could hear engines below, not tanks charging forward, not artillery announcing a new battle, work, diesel under load, tracks grinding, steel against stone. The sound meant the attacker had reached the obstacle before the defender's expected pause had even begun. It meant someone was already turning the broken ground into another route. The German engineers were still dangerous. Their demolitions still killed, delayed, diverted, and exhausted the men who followed. The rivers still had to be crossed. The mountains still had to be climbed. But the old equation had changed. Destroying a road no longer guaranteed that the road would stay functionally destroyed for the amount of time the defender wanted. The new contest was not simply destruction against construction. It was one timetable against another. And down in the river valleys of Italy, the American combat engineers kept bringing machines, steel, fuel, and men to the exact places where the German timetable expected emptiness. Before dawn, the bridge could still be lying in the water. The road ahead could already be coming back to life.